Drops the flag. You published, ready to go?
You ready? Okay. Well, I don't think Milan needs much of an introduction, but we're certainly happy to have him. Tell us about something that I know extremely little about, carbon divestment strategies. And so I will shut up and let him talk up about it. Are we ready to go?
It's ridiculous how we have to do this, but roll. Well, thank you so much for coming, everyone. We're going to be talking about the history of human civilization, the energy basis of our global civilization, and the climate change in the future. Some of the major sources for this are at the front. There's a lot of depth behind all of it. This is both a summary of basically all of human history and what I've been working on for the last 20 years. I should acknowledge at the outset that while this topic is scientific and numerical, it's also emotional and ethical. We're talking about the future of the world, including our own futures and those of young people who we care about. This talk is at a different zoom level from most presentations of academic work. I'll cover why I did what I did from 2006 to the present, what I learned, and what that suggests about what to do now. So there are really elements of three talks in here. Number one, why is climate change such a problem? Number two, what did I learn about the problem by studying fossil fuel divestment campaigns at Canadian universities? And number three, what can we do to solve the climate change problem? My actual PhD work was on problem 2, but it was chiefly motivated by problem 3. And since this talk is for people who aren't experts in climate change policy, I'll provide enough of an explanation of problem 1 to see why the topic is of interest. And I'll chiefly use my results for problem 2 as guidance for answering problem 3. I've made an effort to find quality sources with reputable figures, but they do come from different places and base years. It's the magnitude more than the details that are important, which is why I'll be writing exponents in red. I'll also warn you from the outset that I'm going to cheat twice in this Blackboard-style talk. In the first instance by using 2 slides in cases where I could not artfully or competently draw the content. All right, so scientists have learned about the long-term climate of the Earth thanks to a variety of paleoclimatic indicators. Sediment cores, ice cores with trapped air bubbles, tree rings, pollen, foraminifera. Biological indicators provide evidence of climate conditions by what species are present where, and also by what isotopes comprise them. Isotopic ratios can be used as proxies for temperature and the amount of frozen ice on Earth. So here's the first cheat. I tried drawing this in different ways, but could not accomplish it with any competence. This is a timeline showing about the last 3 million years. Actually, no. The last part. The whole thing is 500 million years. 3.3 million years ago is where we have the first archaeological evidence of human ancestors using stone tools. 400,000 years ago, control of fire by early humans. 300,000, anatomically modern Homo sapiens emerge. And between 80,000 BCE and 50,000, Homo sapiens leave Africa. The main feature I want to look at for this chart is this era called the Pleistocene. And the main recognizable feature of the Pleistocene, this is temperature on the y-axis, are these recurrent patterns of glaciation and interglacial periods. In the 1920s, Milan Ilnyckyj identified the causes of these long-term climate changes, and it's because the Earth's orbit varies between being more circular and more elliptical on a 405,000 year cycle. The rotational tilt of the Earth shifts over a 41,000 year cycle, and axial precession and apsidal precession add cycles of 25,700 and 112,000 years. It's also notable that at the end of the Pleistocene, many global megafauna, large animals, have been rendered extinct, possibly because of human hunting with flaked stone spearheads and arrowheads. This may be where humanity's impact on the biosphere began. Incidentally, the big error in the film Jurassic Park is the idea that the humans would need protection from the dinosaurs and not vice versa. This period, which we'll be looking at on the long chart, is the Holocene, the most recent geological era. And the main thing to note about it is, compared with the past, remarkably stable. Now, it may be coincidental that human civilization has emerged and endured through this period, but I would say that the relationship between civilization and that stability is cause for concern about the future.
Can I just quickly ask? So it's flat and stable here, but also the time scale is expanded relative to the previous panel.
That's true.
So if we were to expand the time scale by the relevant factor, how unusual would the Holocene look compared to that?
Yeah, so in the absence of human-caused climate change, we would be in one of these interglacials and heading back toward a glacial period. But the magnitude of our greenhouse gas emissions are so far beyond these orbital changes that we've prevented that next ice age and then some. Let's get into the Holocene. Now, timelines vary by source and around the world. But some of the major events of this period include the cultivation of grain, domestication of animals, and agriculture meant surplus calories, which means both population growth and the potential for specialized laborers, each of whom requires subsistence agriculture in order to support them with food calories. At about 10,000 BCE, the global human population is estimated at 1 to 10 million individuals. So something between an Ottawa and an Ontario. By 8,000 BCE, there's archaeological evidence of villages on the Tigris and Euphrates rivers in Samaria. 3300 BCE, often identified as the beginning of the Bronze Age, which persisted until 1200 BCE. This included the development of writing in Mesopotamia and Egypt, and the Egyptians were astronomers too. They set their calendar using the rising of the star Sirius in June to be able to predict when the flood would happen. And the flood was crucial to their entire civilization. That was the source of the irrigated agriculture that produced the surplus calories that supported their entire civilizational structure. And that agricultural surplus brought all the trappings of civilization, not just specialized laborers, but tax collectors, police, bureaucrats, a whole centralized hierarchical administration. Around 3000 BCE, we have the use of the plow in agriculture and the construction of Stonehenge. And the Old Kingdom in Egypt began around 2700. In 753, Rome was founded. Setting a pattern for the next many years. In 455, Rome was first sacked by the Vandals. Which would happen again by the Visigoths under Alaric in 410 BCE. By the year 1, entering the Common Era, world population is about 150 to 300 million. In 1001, Leif Erikson, the Norse explorer, became the first European to settle in the Americas. Columbus, eat your heart out. And by 1505, Martin Luther has initiated the Protestant Reformation. Which is important much more than theologically, because it coincides with printing and the rise of mass literacy. 1577 is the hinge point in our timeline. This whole era back here is the era of muscle power, with some windmills and water mills for basic purposes like grinding grain and raising water. And back here, it's about 37 years per centimeter. But as we get into the fossil era, this is just 1.2 years per centimeter. And back to our theme of inconsistent x-axes. 1577, because according to Rhodes's History of Energy, this is when the English Midlands began transitioning into being a fossil fuel society, as coal use broadened beyond blacksmiths, soap boilers, and lime makers. 1648, the Peace of Westphalia. This is where the modern nation-state system essentially emerges. The major elements that we associate with modern states. One geographic region controlled by a single political ruler who outranks any religious authorities and has the right to conduct diplomacy and make war. That state system is what we're still using to try to solve climate change. 1660, we're into the scientific revolution. The Royal Society is founded, and Newton publishes his Principia Mathematica. 1699, Thomas Savery demonstrates a steam engine to the Royal Society. But in one of the examples of how things may happen out of the expected order, it was in 1742 that the first water-powered cotton mill in the UK opened. Some critical changes here. Water power had been used for millennia for things like milling and irrigation, but the extensive use of motive powers from water wheels to power factory-style facilities constituted a mini-industrial revolution before the full age of coal and steel. 1750, we've reached Newcomen and Watt's increasingly efficient steam engines, which added cold water injection and a separate condenser, respectively. Both of these types of engines were initially intended for draining water from mines, coal mines specifically. And they were so effective at it that they reduced the cost of coal. And since coal was the major input to iron production, that reduced the cost of iron, which reduced the cost of trains, which reduced the cost of coal. This kicks off that exponential increase in energy use that we're still living with. In 1764, the spinning jenny was invented to automate thread making, which had been the most laborious part of textile manufacture back into antiquity. So textiles become much cheaper and more accessible. People have better quality and newer clothes, and large numbers of people in traditional textile industries cannot compete economically with the mechanized approach. By 1767, the first tram road had been built in the UK, carts on cast iron wheels pulled by draft animals on adjacent paths. And by 1788, iron production in the UK is doubling every 8 to 10 years. Another of those exponential kickoffs. In 1804 was the first time a steam engine pulled freight. And by 1815, there are 30 kilometers of gas mains in London. And Westminster Bridge is gaslit by night. Between 1821 and 1832, progressively more sophisticated electric motors were invented. And by 1820, the world population had reached its first billion. 1826, the first internal combustion engine patent is awarded to the American Samuel Morey. And in 1830, the first passenger railway opens. Between Liverpool and Manchester. The electric telegraph is invented in 1837. The Bessemer process, which enabled the mass production of steel in 1856, also the first oil refinery in Romania. By 1869, the first transcontinental railroad had been completed across the US. And by 1878, the first commercial telephone exchange had been established in New Haven, Connecticut. In 1879, Edison patented his light bulb. By 1886, Great Barrington, Massachusetts had become the first city in the world with a centralized power grid. 1892 was when the first gasoline tractor was patented, but in 1909, still, half of the land in New England is devoted to growing hay for horses.
Half of the agricultural land or half of
Half the agricultural land, that's right. By 1914, there are 1.7 million internal combustion engine cars in the United States, compared to 8,000 in 1900. By 1925, the world population is 2 billion. In 1942, the Big Inch pipeline was constructed from Texas to refineries on the US East Coast, capable of carrying 335,000 barrels of crude oil per day. That pipeline still operates, underlining the point about how fossil fuel infrastructure is extremely long-lived. 1952, first ever nuclear reactor accident. Can anyone say where?
Vermont.
That was the 70s. The first nuclear reactor accident was the NRX reactor in Chalk River, Ontario, on the road from here to Ottawa. It was actually cleaned up by the US Navy under Jimmy Carter. But in 1957, that was when the first commercial nuclear generating station was established at Shreveport. So the first accident is before the first commercial nuclear generating station.
Well, there were accidents in Los Alamos.
Not reactor accidents. There was the Slotin criticality incident, and I'm sure there were people who, well, we'll stay more on track. Also, 1957 is the launch of Sputnik. By 1959, the world population is 3 billion. Then, by 1974, 4 billion. 1987, 5 billion. 1999, 6 billion. By 2012, we reached 7 billion. So humanity has gone through a series of primary fuel sources. Wood produced more energy than coal until about 1880. Coal peaked in around 1920. Oil peaked in 1975. And gas may be peaking now. Okay, so that was our first act. We can cycle the camera. And Maria has kindly lent me her enormous chalkboard eraser. It's fun, it's like the Zamboni.
Yeah, you can see how hard she works.
Yeah.
But I think she uses water.
Yeah, maybe a little bit better.
Yeah, but when it won't dry quickly enough, put right again right away.
It's usually kids riding around the Zamboni too. Well, kids don't do that.
This- Whatever you just wrote is a lot more visible because the board is really clean. So, the surface of the sun is about 5,525 degrees Kelvin. Which means it has a peak wavelength of about 500 nanometers. So this is shortwave radiation in the visible spectrum, light which you can see with your eyes, the light which Newton split with his prism. The Earth's surface is about 288 degrees Kelvin. So it has a peak output of about 10,000 nanometers, which is in the infrared. That's long-wave radiation. Our bodies also glow in the infrared, and there are some animals that use it to perceive heat in the dark. Now, if the incoming and outgoing energy flows are balanced, the Earth's temperature remains constant. That's just constant macroscopic properties. If on average X joules of energy are entering the Earth system as visible light, if fewer leave, then the Earth system gains energy, it rises in temperature, and it radiates more in the infrared until it's again in energy balance. The composition of the atmosphere affects the outflow of long-wave radiation. Specifically, greenhouse gases like water vapor, CO2, and methane trap energy and prevent it from radiating into space. Multiple lines of evidence, including paleoclimatic records and climate models, suggest a climate sensitivity of about 3 degrees Celsius for each doubling of atmospheric CO2. So if you go from the pre-industrial level of 280 parts per million up to 560 parts per million, you would expect 3 degrees of global temperature rise. This estimate has remained remarkably stable as climate science has developed. It was the central estimate of Arrhenius and the 1979 Charney report, and still in the modern IPCC estimates. But it incorporates only fast feedbacks, not those that take place over decades, like the loss of sea ice or pushing the Amazon rainforest into savanna. There are savage dangers in the climate system. As the paleoclimatologist Richard Alley describes in detail, the climate record contains abrupt shifts where conditions jump rapidly from one state to another instead of shifting gradually. As climatologist Wallace Broker put it, the climate system is an angry beast and we are poking it with sticks. The reason why relatively small changes in solar irradiation from orbit changes produce such big temperature effects is because the climate system includes multiple self-reinforcing feedback effects. For example, hotter temperatures melt ice, which removes a reflective surface, which leads to more energy being trapped in the Earth system. There are also enormous amounts of methane stored in permafrost and subsea clathrates, and causing these to melt would add a lot of warming on top of the direct effects of our fossil fuel use. Chapter 2 of my dissertation provides a detailed account of why warming of well beyond 2 degrees is such a threat. But here I'll just quote Kevin Anderson and say, quote, "It is fair to say, based on many and ongoing discussions with climate change colleagues, that there is a widespread view that a 4 degrees Celsius future is incompatible with any reasonable characterization of an organized, equitable, and civilized global community," unquote. We've already raised CO2 levels higher than at any point in 3.3 million years, going back to the Pliocene when temperatures were 3 degrees Celsius hotter and sea levels were 20 meters higher. We're headed toward catastrophe, and as the joke goes, if we don't change direction, we might end up where we're headed. Act break. Thank you. So, we've climbed the scale of history. Now we're going to climb the scale of energy, getting a feel for energy at the civilizational scale. So our major areas of energy use: transportation, heating and cooling, lighting, agriculture, manufacturing and raw materials like steel and cement, and the computers and gadgets that we all enjoy. The Système International unit of energy is the joule. And 1 joule equals 1 watt per second.
No,
1 joule?
1 watt second, sorry. 1 watt times a second. Watt is a joule per second, so watt seconds is a joule.
I think using a watt for a second takes up a
which
joule.
is a multiplication, not a division, just to be clear.
It should be W times X,
Yeah.
not divided by X. There you go.
Sorry.
1
Units are,
joule is about the energy it takes to lift up a newspaper off the ground. And a human body at rest uses about 100 joules per second. 1 match, or 10 minutes of cell phone use, is about 10 to the 3 joules. 8 hours of hard manual labor are about 3 times 10 to the 6 joules. One kilowatt hour is 3.6 times 10 to the 6. Which, for reference, in Ontario costs between 8.7 and 18.2 cents, depending on the time of day. Heating water for a 15-minute shower is 9.5 times 10 to the 6. One day of food intake at 2,400 kilocalories is 10 to the 7. And the average daily energy consumption in the United States is 10 to the 9 joules. Which, for comparison, is 300 times more than those 8 hours of manual labor. Taking off in a Boeing 777, 1.1 times 10 to the 10 joules. And that's equivalent to daily food calories for 1,000 people. Taking that same jet up to cruising altitude, 4.1 times 10 to the 10 joules. One implication here is that it's only the immense energy density and content of fossil fuels that make this sort of convenient transport possible. Let's get into some of the really big numbers. 6 times 10 to the 16 joules. That's 1 month of US oil imports. And monthly US energy generation is 10 to the 18. That's electricity production. Yearly global energy use, I guess I'll squeeze into the bottom. 5.76 times 10 to the 20 joules. So going through the forms of energy that human beings make use of, I'm going to list the world energy types in exajoules. Which are 10 to the 18. Electricity is at 63 exajoules. Oil, 196.
Is this per year?
Yeah, world use per year. Coal, 156. Gas is 137. All the world's hydroelectric generation, 13.9. All the world's nuclear generating stations, 8.7. All the wind farms in the world, 2.57. And all the solar, 0.72. These figures are approximate and don't fully reflect the rapid recent growth in renewables, but the headline is the same. Humanity gets 20 times more energy from fossil fuels than from all other sources. Second sheet. Next slide. It's easy to get fixated on the forms of energy use that impact our own lives directly. Thinking about the climate change problem, people often fixate on just cars, just electricity. But what this chart from the World Resource Institute shows is all the major areas of human activity: transport, electricity and heat, industry. A further breakdown by type, like cement as a fraction of these different sectors, and then the greenhouse gas inputs that are affecting the climate system. This enormous carbon dioxide wedge, but also methane, nitrous oxide, and other GHGs. So some of the implications: the world remains deeply fossil fuel dependent, and solving climate change is not just about replacing cars or even changing where we get our electricity. All the vital uses of energy must be addressed.
Milan, can I ask, what is the distinction between electricity and the other things?
One is usage, the other is generation.
So of course the electricity is generated from other energy sources. The point of including it is to show that most of the oil and coal aren't used for electricity generation. They're used for transport, heating and cooling, industrial processes. So even if we could green our entire electricity system, there'd still be major areas of fossil fuel use that need addressing.
Thank you.
Incidentally, we're not going to get into this too much given the length of the talk, but there are a few reasons why if we want to stabilize the climate, we actually need to produce much more energy. One of those is global equity. It's neither politically feasible nor ethical to say that people at very low development levels should just stay there for the sake of the climate. But also, we need vastly more electricity to replace some of the usages that currently fossil fuels serve, whether that's gas-fired boilers, petrol-powered cars, etc.
Not as much more as the numbers would suggest, because the electrical uses are usually so much more efficient than the direct fossil uses of that energy.
Yeah, there's some really interesting figures on that in McKay's book, which we can talk about after I've gone through the script. So, fossil fuel reserves versus the global carbon budget. Why don't we put another act break here? So because of the known relationship between greenhouse gas emissions and degree of warming, we can construct a global carbon budget that specifies how much fossil fuel we can still use and have a certain chance of remaining below a set temperature threshold. In 2014, the Carbon Tracker Initiative calculated that to keep the chance of exceeding 2 degrees Celsius of warming below 20%, the remaining global carbon budget is 565 gigatons of CO2. By comparison, the world's known proven fossil fuel reserves are 2,795 gigatons. 65% of that is coal. So vastly more than is compatible with remaining below a 2-degree threshold. In 2015, the IPCC estimated that 600 to 800 gigatons of further emissions would melt the West Antarctic ice sheet, which would eventually produce 4 meters of sea level rise. Just to put that in context, that's most of the Netherlands gone, along with a giant area of coastal China, much of coastal Florida, and damage to ocean-side cities around the world. In their 6th assessment report, the IPCC cited that about 2,500 gigatons of cumulative CO2 emissions have taken place from 1850 to 2019. They modeled a range of future scenarios. In the most aggressive mitigation scenario, which is the most politically optimistic, they foresaw 500 gigatons of further emissions. And they projected that to cause warming from a bit over 1 to perhaps 2 degrees Celsius. At the high end, they modeled scenarios where 2,000 gigatons of further emissions are undertaken, producing at least 2 and probably more than 3 degrees of warming. In summary for policymakers,
Sorry, what you just said doesn't sound consistent with what you said before of a 5.6 gigaton budget to keep warming below 2, and then you quoted some numbers that are higher than that and said that they would.
Sorry, this is 565, not
Okay.
5.65.
Thank you.
I couldn't clear that. In the summary for policymakers at the IPCC's 6th assessment report, they said, quote, projected CO2 emissions from existing fossil fuel infrastructure without additional abatement would exceed the remaining carbon budget for 1.5 degrees Celsius. So if we just use all the coal, oil, and gas fields that are already in production, that would blow the carbon budget. And of course, everybody is building more, whether they're developing countries, long-standing fossil fuel producers. The fossil fuel bonanza is ongoing worldwide. Some implications. If we're serious about staying below 2 degrees, we should not keep developing fossil fuel reserves. And there is the potential for trillions of dollars of past and future investment to be wasted if we invest in long-lived fossil fuel assets that we're then going to have to scrap before the end of their economic lifetimes. Now, what I'm saying is basically that climate stability equals fossil fuel abolition. There's basically no kind of research that's more welcome to the fossil fuel industry and its supporting governments than the idea that CO2 can be profitably reused or at least cheaply buried. This is how they hope to break this identity between climate stability and fossil fuel abolition. But right from first principles, is it plausible that carbon capture and storage will address any substantial fraction of our greenhouse gas pollution? Global oil production in 2022 was about 4.4 gigatons. Every oil field from Alberta to Saudi Arabia to China. Whereas our CO2 pollution in the same year was 37.2 gigatons. So if you wanted to bury all that CO2, you would have to replicate the global oil industry 8 times over. And your new carbon capture industry will only cost money and only cost energy instead of producing either. As I put it in a 2021 letter to the Minister of Environment, climate change mitigation is fossil fuel abolition, difficult as that will be in an economy that is as dependent on the sector as Canada. Carbon capture and storage has one real purpose, giving industry and governments an excuse to delay action on replacing fossil fuels.
Did you get a response?
None of the ministers of the environment who I've ever written to have responded. It's democracy. All right. So now the important part. How do we get out of this hole? Sounds like there's a question. Sorry. Is there a question? Ghosts in the AV system. That's fine. Okay. So part 3, the climate safe energy system. Start putting some encouraging numbers up here. 200 watts per square meter is the typical incident solar energy at a mid-latitude location, average over a 24-hour cycle. For space enthusiasts, it's 1,400 watts per square meter in orbit. And given the audience, well actually first, total solar energy incident on Earth in a year is 1.74 times 10 to the 20 watts, which over a year is 5.49 times 10 to the 27 joules. Now, of course, that would involve covering the entire Earth's surface with 100% efficient solar cells, but it gives us a sense of scale. All fossil fuels produce energy by breaking chemical bonds. 1 kilogram of coal has about 24 megajoules of energy in those bonds. 1 kilogram of gasoline has 46 megajoules. 1 kilogram of uranium-235 through fission can yield 76 billion megajoules. So on a whole different order of magnitude. And this one's just for CITA. Total solar power output is 384 yottawatts, which is 10 to the 24. And over a year, that would be 1.2 times 10 to the 31 joules. So Dyson sphere enthusiasts, there's a lot of energy to go chasing for. The best source I have found for a comprehensive and numerical assessment of humankind's energy options is Cambridge professor David McKay's Sustainable Energy Without the Hot Air, which is available online for free. On the demand side, McKay notes that average UK energy use for all purposes, from making the steel that goes into the buildings that you live in to making the fertilizer to grow your crops, is about 125 kilowatt hours per person per day. Which gives us something to aim for in terms of what our energy alternatives are. What about wind? If you cover the windiest 10% of the entire UK with onshore wind farms, this is paying no attention to local opposition or the economics, you get about 20 kilowatt hours per person per day. Which incidentally would require rebuilding all the wind that exists in the world today in the UK. And also for comparison, that 20 kilowatt hours per person per day is half the energy use the average driver uses just for driving. One of the, I think someone must be on the same frequency as our wireless microphone.
I mean, we're not talking to Zoom or anything. This is just, yes.
Aliens.
I'm showing my last slide, so you can go step off. With offshore wind, if you're willing to fill an area the size of Wales with wind turbines, that gives you 16 kilowatt hours per person per day. And if you're willing to go deep offshore and put a 9-kilometer strip of wind turbines around the entire UK, that would give you 32. Covering 5% of the entire UK with solar photovoltaic, which would be 200 square meters per person, that would yield 50 kilowatt hours per person per day. Whereas capturing every wave on the entire UK coastline would only give you about 4. Building every feasible tidal stream farm, tidal barrage, and tidal lagoon would give 11. And exploiting all the hot, dry rock geothermal which is possible in the UK would yield about 1.1 kilowatt hours per person per day for about 800 years until the rocks cool down. I haven't seen the equivalent of McKay's calculations for Canada, but with half the population and a lot more land area, the renewable power potential per person will be greater. Nuclear plants in the UK provided 2.6 kilowatt hours per person per day, whereas in Canada it's 7.4, 7.5 in the USA. In Sweden and France, they get 19 kilowatt hours per person per day from nuclear plants. So if you were to quadruple the world nuclear fleet from about 400 reactors to 1,600 reactors, that would give everyone alive about 7 kilowatt hours per person per day. One of the ways to capture those big solar numbers, instead of using mid-latitude locations, go to the sunniest locations, build gigantic solar facilities. If you built a 600-kilometer by 600-kilometer concentrating solar thermal facility, it would provide 125 kilowatt hours per person per day for everyone in Europe and Africa, for 1 billion people. Or you can give 500 million people an American lifestyle at twice the energy level. So some major takeaways. Prior to the Industrial Revolution, energy use in the UK per capita was about 20 kilowatt hours per person per day, which relied on burning 4 kilograms of wood per person and having 10,000 square meters of forest per person to supply that. As I mentioned, the average American is using 250 kilowatt hours per person per day now. McKay's estimate, building the maximum physically possible amount of all renewables, ignoring economics and public opposition, would yield about 180 kilowatt hours per person per day for people in the UK. But looking at some more plausible estimates, the UK Institute of Electrical Engineers estimated plausible renewable production at 27 kilowatt hours per person per day. And when McKay does factor in what he thinks the public would tolerate, his estimate is 18 kilowatt hours. So that's 15% of use. If you want to replace fossil fuels with renewables, you need to industrialize the landscape. And the only real options for maintaining energy-intensive lifestyles like those in rich countries today are nuclear along with country-sized solar and wind facilities. But on that nuclear question, I have to say, nuclear power has some substantial and unique advantages in the fight for climate safety. Inexpensive and plentiful fuel, low marginal cost of production, a proven capacity to output power 24/7, and a proven ability to produce power at gigawatt scale for decades. In the United States in 2016, nuclear plants produced about 20% of their electricity with a capacity factor of 92.1%. The average nuclear plant was providing its output nearly 93% of the time. In comparison, capacity factor for dams was 38%, for wind farms 34.7%, and for solar photovoltaic just 27.2%. 2013 work by NASA's Goddard Institute estimated that global nuclear energy has avoided 1 million air pollution deaths and 64 gigatons of CO2 pollution so far. And they estimated that by replacing other energy sources, more nuclear could avoid 80 to 240 gigatons of CO2 emissions by 2050. The term dual use is applied to technologies like those in nuclear energy that conceivably have both civilian and military purposes. But the fact is, there's no such thing as purely civilian nuclear technologies. If you can spin uranium-235 up to 2% enrichment for your light water reactors, you can spin it up to weapons grade. And all civilian nuclear reactors breed plutonium, which provides a back pocket nuclear capability for anyone who's operating them. The world is experiencing a nuclear arms race with the prospect of multi-state breakout proliferation in the Middle East and Southeast Asia particularly. So in summary, nuclear fission has unique capabilities and singular drawbacks. This is going to be my second and larger sheet of the presentation. To fit the context of all this in an hour-long talk, I had to cut the section about my own research to practically nothing. However, you can get a 10-minute summary from the recent talk I gave to the CITA conference, and every part of my dissertation contains its own summary. But in ultra brief, the campus fossil fuel divestment movement encouraged organizers to adopt an intersectional climate justice perspective in which climate change is seen as one symptom of systemic global injustices like capitalism, colonialism, and racism. This helps them to overcome some of the structural barriers to action by linking climate change mitigation to more personally useful objectives closer in time. It's always a challenge to maintain a focus on climate change when most political problems seem more urgent and perceptible. One big drawback of this emphasis on intersectionality, progressive left activists don't realize how unpopular their proposed course of action is. For example, there is a movement advocating degrowth, which is a phenomenon we already had a word for, impoverishment, and it's neither popular nor glamorous. So as a corollary, progressive climate change policies risk being reversed by the next change of government and doing no good. We're talking about a timescale of decades and centuries. A government of 4 years doing the right thing and then getting shifted out won't produce any long-term benefit. So to wrap up, the problem is political, not scientific. The biologist E.O. Wilson said, "The real problem of humanity is the following. We have Paleolithic emotions, medieval institutions, and godlike technology. And it is terrifically dangerous and now approaching a point of crisis overall. We have all the scientific evidence we need, from paleoclimatic records, observations, and climate models, to be confident that proceeding with business as usual will radically destabilize the climate, human civilization, and our lives. We also have the technologies we need to abolish fossil fuels while providing high quality of life lifestyles to everyone on the planet. But, of course, they all have costs and drawbacks. We're being blocked for political and economic reasons. The fossil fuel industry and fossil fuel producers would lose trillions from a successful transition. We also face structural barriers at all levels, from our individual psychology to group sociology to world politics. Overcoming these barriers and abolishing fossil fuels is the only path forward to a future that we would want to live in. Greta Thunberg's address to the UN Climate Action Summit in 2019 is an incredibly raw and poignant moral rebuke. Quote, "You have stolen my childhood and my dreams with your empty words. You're failing us, but young people are starting to understand your betrayal. The eyes of all future generations are upon you, and if you choose to fail us, I say we will never forgive you," unquote. She went on to emphasize the immense potential risk of self-reinforcing feedbacks and the existential stakes involved for young people. Quote, "The popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees Celsius, and the risk of setting off irreversible chain reactions beyond human control. Maybe 50% is acceptable to you, but those numbers don't include tipping points, most feedback loops, additional warming hidden by toxic air pollution, or the aspects of justice and equity. They also rely on my and my children's generation sucking hundreds of billions of tons of your CO2 out of the air with technologies that barely exist. So a 50% risk is simply not acceptable to us, we who have to live with the consequences." Thank you. Actually, have a lot of time for questions. Well, it's on. Yes.
Do you have numbers for the average energy usage for different demographics, say working academics versus the average person?
I'm sure they exist, not off the top of my head, but I suspect it's one of those power law things where the top 20% use 80%, and the top 1% use 10%, something like that. Yes?
So this 125 kilowatt hours per person per day, that's that's Britain, right? And Europe in general is similar, is that right?
Yeah.
So what's the main difference between North America and Europe? Is it like transit, or is their food system more sustainable than ours?
Yeah, it'd be interesting to see an item by item breakdown. Certainly some of the major factors are just population density, how close people are to each other.
Yeah.
It's, the post-1950s suburbia that has contributes a lot to why the US figures are so high. So much indoor space per person and so much travel from place to place.
Is there any way to ever get rid of the horrible suburbia that surrounds every city in North America?
That would be an interesting talk for a subsequent session.
Can I just comment on that? So there's a widely shared graphic which shows evolution of greenhouse gas emissions between the G7 countries and from 1990 to 2022, and Canada's wobbles, but basically goes up by 16 to 20% over that time period, while the UK's drops the most of the G7 by over half. So the UK emissions actually dropped significantly since the time that McKay published his book, because that was the late 90s, I think, early 2000s?
I think it's 2006.
Okay.
Yeah. One of the endless complications of any kind of greenhouse gas accounting, say Britain goes from making steel domestically to importing South Korean steel. The way we almost always count emissions, now those count as South Korean emissions, not British ones, even though the British are using the steel. So there are flows of embedded emissions in trade flows that can mislead when it comes to per capita emissions. Similarly, if you look at fossil fuel producers, if you attribute all of their production emissions to the population, places like Qatar look like they have insane per capita emissions.
Well, I think most of the rise in Canadian emissions is coming from that.
Yeah, if you look at the history of Canadian emissions over the last 20 years or so, there have been some big cuts, most importantly through phasing out coal in Ontario and elsewhere, but the growth in the oil and gas sector has been so great that it's swamped everyone else's efforts to improve.
So to what extent is that decrease in British carbon output just due to them exporting development? Because they don't make anything there anymore, right? So, like,
I don't know. They're
how-
still developing North Sea oil.
Yeah.
And that's
Like
one of the
other manufacturers.
irresolvable conflicts here. So if we're talking about the global carbon budget, different groups are going to make their cases. Someone like Venezuela or Chad or any low-income country can say, back to 1750, all you rich countries have been burning all the coal you want, you've done your economic development on that basis. Our historical emissions per person are way, way lower, so whatever's in the carbon budget, we should get it. Then countries like Canada say, well, we have all these environmental and labor standards, we've got this green ethical oil, so if there's going to be 565 gigatons of fossil fuel produced, we should get that share of the production. And then Saudi Arabia will say, are you nuts? You're using natural gas to make synthetic crude when we can just stick a pipe in the ground and have crudes shoot out for $5 or $7 a barrel? Like, there's no way Canada should have any part of the global carbon budget. It should go to the people who can produce the fossil fuel for nothing. And all those positions are right, but of course incompatible with each other or a finite carbon budget. Takes us back to that Peace of Westphalia point. We live in a world where sovereigns are nation states and can't insist on other sovereigns doing anything and find it very difficult to coordinate on anything that requires immediate sacrifice from everybody. Yes?
I'm just wondering, is there any estimate about the potential increase of CO2 production under the AI revolution?
Yeah.
You know, projections about the future, very speculative. You can make a case that it will increase emissions or that it will decrease emissions. As with so many technologies, it's a question of which purpose we put it to. If you were working hard to optimize reducing energy use and applied your AI capabilities to that, I'm sure it could help you. But if you're just adding it on top of everything else without a particular plan to reorganize your energy system, it is an additional energy draw. And it will likely have all kinds of unpredictable effects. We talked about some of the labor effects of the Industrial Revolution. There's been endless commentary about how thinking machines will give us the intellectual labor equivalent. Like, what happens if 20 years from now there's an AI that's better at every part of astrophysics or politics than any human can be? Yeah.
Yeah, in your research, did you find anything in terms of nuclear that did not involve uranium and plutonium? And I've heard you talk in the past by that, like thorium and stuff, but...
You can use thorium, you can use breeder reactors, but there's so much uranium that it just hasn't been justified. There's enough uranium to power our global civilization for centuries, if not millennia. Especially if you ever figure out how to separate it from seawater.
Right, and then it just goes back to the political, like proliferation of nuclear weapons and stuff like that.
Yeah, there are lots of special risks with nuclear. People don't like being sited near it because of the risk of accidents. People are wary about the fuel, which some of will remain dangerous for millions of years. And it's intimately connected with nuclear weapons. Like, the first reactors that were built that weren't fully experimental, like Enrico Fermi's Madison-Port reactor. The first reactors that were engineered and constructed at the Hanford site in Washington State were for breeding plutonium. The first British reactors and the first Russian reactors were for breeding plutonium for weapons, not for electricity production. And in fact, Stephanie Cook has a book called Immortal Hands, where she estimates that in the nuclear weapon states, like the US and UK, because they optimize their reactors for plutonium breeding, and because a reactor that's not producing electricity takes a lot of electricity to run, on balance, she argues that in those states, nuclear has actually taken energy out of the grid rather than contributed any, because so much went into making plutonium for bombs. Yes?
I was wondering about all the universities in Canada and other places that have divested from fossil fuels. What are they spending that money, or how are they diverting those funds? Is there any information about that?
I mean, it's really just a conjuring trick. Universities don't tend to directly invest in stocks in the first place. They have asset managers who buy whole tranches of different types of assets. And of course, any stock you sell just gets bought by somebody else. The aim of the divestment movement was not that universities selling stock by itself would have any economic impact on fossil fuel firms. In fact, a firm's stock price by itself doesn't have any impact on their ability to invest or operate. The hope was, by saying we don't want to invest in these things, they're saying we've already got more than the fossil fuel infrastructure we need to stay within a safe carbon budget, so building more will just be wasted. And that as moral leaders, universities would say, you know, this is this deceptive industry that's manipulated our politics, manipulated the public. We don't want to invest in them for moral reasons. And there was the hope that that would delegitimize the fossil fuel industry. The one challenge there is when it comes to public opinion, the fossil fuel industry is already basically rock bottom. You all fundamentally rely on it to stay alive, but if you ask people what they think about it, they're already about as averse as they can be without actually wanting to do anything to shut it down.
I think that must vary from place to place.
Yeah, we were just watching an Oilers game here last night.
Yeah, sure. Yeah, and that's yet another of the many political challenges. There are places all around the world that have long established fossil fuel-based economies on the production side, and it's very disruptive for them to consider transitioning. Yeah.
So, yeah, thanks for the talk. It was really interesting. I guess some expertise you have that I definitely have very little knowledge of, I think, is more like policy side things. So I'm curious, like, broadly, what you see, like, for a smaller country like Canada, economically small, like, what would you say is like, what would you see as kind of the best sort of action that a country like Canada could take to influence this? Because obviously we're a small piece, like, proportionally we're very bad, and so we could obviously fix that, but we're still a small piece of the landscape. So, like, what's like the ideal thing a country like Canada could do? And then also, what is feasible given that we're incredibly heavily invested in?
Well, let's not forget not just investments, but subsidies. I mean, Canada subsidizes its fossil fuel extraction quite significantly, buys pipelines and such.
From a pure theory perspective, the economist way of solving this problem is, if greenhouse gas emissions are harmful at some level, set a price at that level, or actually at the level that it will take to stop those emissions, and that will lead to people saying, well, you know, I don't really need my patio heater, it's not worth paying the carbon tax for it, so I won't do that. Or, you know, it sends a signal through the whole economy to deprioritize fossil fuel use. But setting that price at a level that's high enough that it will start driving fossil fuel abolition will be very disruptive and unpopular. It's not just something that happens in the background. The whole point is it's there to force you to change how you live. I mean, on the technological side, there are lots of major improvements we can make. Obviously, someone was talking about electric motors being so much more efficient than fossil fuel ones. That's true. Heat pumps are so much more efficient than conventional heating and cooling. And another element of economics that's worth considering, fossil fuels kill millions of people globally through air pollution. So if you use a reasonable estimate for the value of human lives, there's a strong case to be made for fossil fuel abolition just on that basis. But as with climate change, it's one of these situations where the problems spread out everywhere, You can't say that that person died of emphysema because of this specific coal plant. The costs being borne because of that air pollution are comparatively small and borne by everybody. And then the benefits of producing that pollution are concentrated, and there's just a few people who keep fighting for their right to do so. And the fact is, I don't think anyone has a clear political path forward for dealing with climate change. I'm getting into pure speculation, but my sense, based on my work over all these years, neither the general public nor our politicians are willing to mitigate. They just are not willing to do it. So we're going to be locking in 2, 3, 4 degrees Celsius of warming in terms of the CO2. But there are lags in the climate system. One of the many complexities I wasn't able to get into. It takes decades for the CO2 emitted today to have its full warming effect. So in an approximate sense, we can say that this heat wave, the warming we're experiencing now, this is the 1980s catching up with us. And if you want to look at what our CO2 production did in the period after that, things are guaranteed to get much, much worse.
Half of all of the emissions in your timeline was since 1990. So if it's the 1980s catching up with us, that's not even the first half.
Yeah, so on that basis, I find it hard to believe that in 10 or 20 years we're not going to be deliberately geoengineering with all the risks and downsides that involves. But it's totally impossible to predict. There's the fact that it's always hard to predict the future, in fact, literally impossible, but that's even when it's just the future within an overall paradigm that's equivalent to what you've had in the past. We have no past experience for anything like what it would take to resolve climate change, or for what radical climate change would do to humanity.
Can I just comment on the question of what can Canada do? One of the questions that you might ask is, what would it take to get Canada to do anything? Because Canada, regardless of what the public, whose presentation is the top emitter in the G7 and subsidizes the fossil fuel industry and, does not take proactive action on any of the fronts just by participating in the process. So I think, the real question is, what does it take to change a country like Canada?
Our leaders are such liars. If you look at these greenhouse gas trajectories, they say we're going to net zero 2030, 2040, 2050. They're in power for 5 years. They have no control over what their successors did. So it's like someone who's trying to eat less or drink less alcohol, telling you, here's my plan. For the next 5 years, I'm going to eat and drink more, and then I'm going to have this cliff that I go over, it'll be super low after that. Like, it's the kind of promise you make if you're fundamentally insincere. And that's the nature of the Paris Agreement commitments and Canada's government's climate commitments. One instructive and terrifying chart from my dissertation here. I'll walk in. So, we've got historical emissions up to this peak, and then different rates at which you need to cut to stay below 2 degrees based on how much longer you delay. And even if we had started in 2020, it would have required much more rapid annual emissions than had ever taken place in the world. More rapid than in the period when the Soviet Union collapsed and, without intending to, lots of their industry shut down. And the more you delay, the more vertical that cliff becomes. So, yeah, we're in a real dangerous, desperate situation as a global civilization. Yes?
Is there any analysis around how carbon tax contributes to the climate change completely in Canada since it was first introduced?
Yeah, it's certainly better than nothing. It deviates emissions from what would have been a business as usual trajectory without it. The issue is the magnitude of that difference and the fact that we're still allowing vastly increased fossil fuel production. The oil sands, Canada's oil and gas sector is more than swamping everything that we're trying to do to deal with climate change. Yes, please.
there's a big international activity called the Fossil-Free Non-Proliferation Treaty, which is having some success in getting countries to, pass a motion and agree with it. Big parliament or in the city of Toronto or whatever. But from what you said, the replacement side is not really equally under control. So people can say we're going off fossil fuels, subsidies, whatever, but if you can't replace that energy, then we're not going to have 125 kilowatt hours per person per day. We're going to have 0.
Well, can I just quickly react to that? Because I think the treaty is about the creation of new infrastructure, and the creation of new infrastructure is something the International Energy Agency and I think also the UN has said is unnecessary and also counterproductive. So I think it's not about shutting down the industry completely immediately. It's about preventing the growth.
Non-proliferation.
Yeah.
It does sound like let's not build more pipeline.
Yeah.
Let's not discover more oil.
Some sort of multilateral coordination is clearly necessary, but obviously really hard. One potentially encouraging mechanism, going back to the carbon pricing and the issue about imports and embedded emissions, the EU is establishing a carbon border adjustment or carbon tariff. So if there's a steel plant in Sweden that's using electricity to make steel, so it's much less greenhouse gas intensive but much more expensive, and your choice is between using that or importing steel from China or South Korea, which at present don't have carbon prices, a carbon tariff would be applied at the border to those imports of non-carbon taxed goods, which would it would have multiple beneficial effects. It would mean that the cleaner stuff produced at home can compete with dirty imports, and because the tariffs would go to the country that the imports are going to, for as long as the exporting country doesn't have an equivalent carbon price, that creates a strong incentive for the people outside to create their own carbon price, because at least then it would go to their government rather than the importing government. And unlike a lot of these worldwide multilateral efforts where you need everybody to get on board and coordinate and act together, with carbon tariffs you could build it out block by block. Like if Europe established one and then added North America and added Japan, we wouldn't need everyone to agree at the beginning for the system to be stable and start sending some good incentives.
You probably have to do it in pretty big blocks though, right? Otherwise you're, would it damage your economy if you're increasing the tariffs on these things?
All these things will have complex economic effects.
Yeah.
And political effects. Don't underestimate the interference and subversion of these things by the fossil fuel industry and the allied political parties. So, Ontario was in a cap and trade agreement with Quebec and California, which was exited under the incoming Ford administration, and those other provinces and states are currently trading and have successfully reduced significant amounts of emissions as a result. At least I think that's as a result. Their emissions have gone down statewide significantly for both places. So,
in the broadest sense, our politics is incredibly dysfunctional on this issue. If you look at Canada, the US, the UK, you've got a center-left party that kind of tries to do the right thing but doesn't do 1/1000th of what they need to, and then a right-wing party that more than undoes the good work of their predecessors. The political debate in Canada now is, should we take the people who are doing way too little and replace them with people who are actively going to make the problem worse? The constituency for fossil fuel abolition effectively does not exist.
but also there's this active effort to undermine and support the undermining of that process. It's not as though this is dysfunctional for no reason whatsoever.
Yeah, one of the strong arguments that divestment campaigns were able to use was the fossil fuel industry has a long-standing record of deception toward the general public and policymakers. I mentioned foraminifera as one of the paleoclimate indicators. Nobody in the world knows more about them than the global fossil fuel industry, because that's how they find the sedentary basins that fossil fuels are in. We now know from their own internal documents that companies like Exxon have been planning their oil platform heights to take into account multi-meter sea level rise for decades. So perhaps that creates some political opportunities for transitioning, but there's really no escaping the incredible convenience and power of fossil fuels. I think that's the big misunderstanding of the intersectional progressive left climate movement. They think that somehow that utility would go away in an alternate economic or political system. But even to the extent that there are alternate economic political systems around the world, you can look at China or North Korea, they still try to produce economic growth. They may not be North Korea may not be very successful at it, but it's still their aspiration. So the template largely doesn't exist.
You said that people really weren't living up to the Paris Agreement. And the Paris Agreement has, it doesn't allow for all of this offshore effect of, say, Canada exporting coal in the past and liquid natural gas in the future. It just doesn't count for Canada. And so it's disingenuous for Canada to say, even if we met our commitments on the tariffs, it would ignore that offshore effect. Right? And it basically gets back to, well, our oil and gas reserves are going to be burned, whether by us or by somebody else. It's bad for the climate, but we get to, polish our, say, oh, well, we're doing a great job, we're getting somebody else to burn it. So, do you think the IPCC will ever come around to getting that right? There's words for, how it's attributed. I forget the fancy words. But you could have a totally different system, which would be focused on let's not have it burned at all, not where it's going to be burned.
Our whole international system of diplomacy, multilateralism, is based on states being sovereign and being able to choose whatever they want domestically. No state can impose anything on any other state.
Except for tariffs.
Well, tariffs are something you charge on imports into your country. It's within your sovereignty.
Well, but everybody that's burning fossil fuels is imposing a bad atmosphere on everybody else on the planet. So it's not like, it's just that doesn't count in the economy, I guess, or the figuring. But, the whole, the bad climate, the raised temperatures, the pollution, they don't know anything about borders. So,
Yeah, it's one of those situations where macro rationality and micro rationality completely conflict. If we could just make the choice for all of humanity, obviously we would start rapidly phasing out fossil fuels and building alternatives. But for every individual in this vast collective who can't control what anybody else does, given that nobody else is doing it, and given that there's no advantage to just you doing it, everyone stays trapped.
Well, I mean, there's definitely a contrast between states. I mean, political oscillations aside, the US did pass the Inflation Reduction Act, which puts a couple $1 trillion into energy transition, and Canada did nothing in the same period. So, yeah.
Technology subsidies can certainly be very important, The reason why wind and solar are as competitive as they are now is because governments, including European governments, especially Germany, but also China, have put probably, I don't know how many billions of dollars into developing those technologies to a commercially mature point. That could also apply in other areas. So there's some hope there.
So I was wondering if you could make a comment on the kilowatt hours per person per day. Again, so in this case, this example of 125 is, I guess, a standard of living of the United Kingdom or Europe, like 15 years ago. And like we would expect that that number would probably just continue to go up.
Except the graph I was referring to has it going down.
Right. And so like, is there, like you were saying before, mentioning about the, this idea of degrowth, which is unpopular. Is there like an idea on what kind of level we could manage as sustainable that would be smaller than 125? That would be like something to aim for. That like, yeah, that's.
Yeah, I really recommend this book.
Okay.
There are basically two types of chapters in the book. There are chapters about all the ways we could generate energy, and chapters about all the ways we can make everything we do more efficient. And he gives some good sort of order of magnitude estimates for how much more efficient something could be made. Like, you can make a car 3 times, maybe 10 times more efficient, but not 100 times more efficient.
Right.
Same for an airplane.
No, airplanes you can only do about 20%. He's very clear on that.
Yeah, well, airplanes are already very optimized for efficiency. Like, one of the misleading things, people think flying is inherently worse than other forms of transport, but in terms of CO2 per passenger per kilometer, it's better than cars and better than trains in Canada even, because trains burn such dirty fuel. It's just that because flying lets you travel so much, it enables people to have these very carbon-intensive lifestyles.
Right, because that's like CO2 per person per kilometer per second, basically, and that makes the airplane better, like more desirable, right? Like you could make trains more fuel efficient in some fashion, but the distance that you travel per time still is not going to really beat a train for the cost.
I think trains are more efficient if you pack them fully, and people just don't pack trains fully in Canada. Like you have a vast passenger compartment or something, and you're going transcontinental. Like a train up and down the eastern seaboard is far less than a flight, and a packed car is also about a quarter of the aviation usage. It's just that driving on your own in an SUV someplace is comparable to flying.
Okay. There are some fun charts in the book showing every form of transport ranked by both speed and emissions per passenger kilometer.
Okay, okay.
I don't think there's anything worse than a hydrofoil, which gives you all the speed-related energy requirements of a plane, plus you've got drag with water instead of air. So hydrofoils are not the answer, that one we know. Okay, well, we can certainly stick around and keep talking, but thank you all so much for coming. And
Can I take a picture of this book here? Mention. You said it was available online too.
Close to the manager, but also.
Is there time to be leaving the